Okay, we're going to go into the labs here. So what I'll do first is I'll take you into a lab where we use an instrument to actually find out the sort of nanomaterials and nanoparticles we look at, actually find out what they're made of, which is a critical question. Hello. So this is basically what we call a mass spectrometer, but the essential tool we use to find out what a substance is made of chemically. So when someone designs, say, a new nanoparticle, something to deliver a drug, one of the critical questions is what's the material on the surface and how it's going to interact with the body, and this is the tool we use to find out what that material is made of. Okay, so this whole instrument is actually called a secondary ion mass spectrometer, and it's designed to deliver a beam of ions towards the surface. That's some small particles. As those particles bang into the surface, they fragment off whatever is on our material, and those materials come out and they're put into a mass spectrometer, which basically separates it out and tells us what each one of those components is made of. The reason it's in this sort of in this steel chamber is because we have to do this experiment under vacuum, so we've pulled all the air out. That's so those ions can travel to the surface and hit the surface. But what this does then eventually is it gives us a spectrum, and you can see a spectrum that's coming out here, and basically each little peak corresponds to a particular type of material on the surface, and we can take that information and then map that on a surface and say what material is where, and that's critical in understanding how, for example, coatings of implants interact with our body. So nanotechnology, most people think about it as being very tiny, a small scale, and that's partly what it's about, but it's also, by making something small, it's important we give it a new property, something different. And so nanotechnology is about not only making things small, but actually having a new function. So, for example, we can deliver medicines we wouldn't otherwise not be able to deliver, simply by making it small. So we have to have instruments like this instrument here, which enables us to analyse those nanomaterials, so we can actually understand, when we make these materials, how they're going to work. Just a simple, so nano is basically 1/1,000,000th of a millimetre. So that's so small that we can't use normal microscopes to see that, so you would not be able to see it with your eye, you would not be able to see it with a normal optical microscope, so we have to use very special microscopes, either electron microscopes, which you can see around here, but also something called an atomic force microscope, which we'll see as we go around the lab. And the key for us is how life and biology behaves at that nanoscale, and that means using a whole set of new tools, which we are expert here at Nottingham. My favourite one is the rate your hair grows. So your hair will grow about a nanometre a second. So that's a nice one. Or you can think about another one is if a seagull lands on a big American aircraft carrier, one of those really big ones, and a seagull lands on it, the aircraft carrier will sink by 1 nanometre. So that kind of gives you the idea. It's obviously very, very small. So that's why we need such special tools to understand what things are made of and to visualise. At that kind of scale, what starts to happen is that materials start to have very different properties. So things before that maybe would have been soft become hard, or they have new optical properties, which is very important, for example, for new flat-screen televisions, or they have new electrical properties, which makes them very interesting for making high-powered computers. So it's as we get to the scale where literally the size of the atom, the fundamental thing we're all made of, becomes important at that scale, then we're at the nanoscale and we have a whole new science to play with. And so it's not about just making things small, it's about giving them that new property as well. Well, obviously something as small as that, then we can't see it, we can't move it around unless we have very special tools to do that. And then we have important things we have to think about in terms of the safety of these things. We can't actually see them, so it's very important that we have measures to control them and understand. For example, if you ingest them or breathe them in, we need to understand what that's going to do. So we're very careful in dealing with these nanoparticles, nanomaterials, because this is a new technology that we are learning as we go forward. So we're going to take you along to a lab where we use the microscopes to visualise the type of nanomaterials we've been talking about. Okay. Okay.
Where are we now?
So basically in one of our atomic force microscopy labs, and this is a special tool that we're particularly good at here, that allows us to visualise nano-sized objects. And very importantly for us, it allows us to image them in liquids and biological environments. So when we're working to develop new medicines or new implants, we can actually look at those materials in the right environment. And that's a core skill that we have here. Whenever you speak to anyone in our area, they're always doing this and saying particles interacting. And when I show you how the microscopes work, basically it really is just a very sharp needle on a, it's kind of like an old-fashioned record player, if people can remember record players, where you had an arm and a needle. The only thing about this microscope is that the arm is absolutely tiny. It's about a fraction of a millimetre in length, and the little point is now basically got a single atom on the end of it. So when we run that needle over the surface, the image we get, the profile we get, is because that needle is so sharp, we can actually see, for example, things like single proteins. So Greg's actually working on a project with the National Physics Laboratory, where Greg is designing a new type of probe that I was just talking about with the needle, and trying to design one that's better for the kind of work that we do. So this is a collaboration between us and physical sciences, which is something we like to do. Actually, this scale is pretty not that small. This is just an optical camera. Okay. But this needle that Greg was talking about, this has the very sharp nano needle behind it. Because nanotechnology is not just about small sizes, it's about small forces or anything that's in the sort of nanoscale. So we actually measure, for example, the forces between individual molecules. So say when two proteins come together, if you think about an antibody, that sort of Y-shaped molecule grabbing something, we can measure those forces. So this microscope here, which actually looks quite small, doesn't look sort of massive or anything, but this has the power to see individual atoms or individual molecules, and it can do it in liquids, which is the key thing for us. So this is an image. I mentioned that we don't always just work with nanoparticles, sometimes we work with even tablets, but it's the structure inside the tablets that's at the nanoscale. And the reason we do that is a lot of modern drugs are very difficult to deliver because they don't dissolve very well. So by making the drug nano size but within a normal tablet, we can actually improve a lot about how to deliver the drug. So drugs that otherwise wouldn't get to the market, wouldn't be used to help people, we can help them do that. This is what we're doing here is kind of a slightly different experiment where, when I was saying we can measure the forces between molecules, so that's what Mudasir is doing here. So what we do now is we bring two molecules together. So this is nanotechnology at its best. We're taking two molecules, we're bringing them together, we allow them to bind, just as would happen in our bodies, a sort of biological process, and then we pull them apart. And then as we pull those two things apart, in this case it's a vitamin and a protein, as we pull those apart we can understand more about the structures of the things as they bind. And that's one of the big questions in biology at the moment, is trying to understand how molecules recognize and bind each other, and how the structure of those molecules helps us understand that. Well, drug delivery normally is about taking a drug that, for example, might have severe side effects and delivering it only to the place where you want it to act. And what that does, for example, if you think about anti-cancer drugs, which have very serious side effects, we think of hair falling out and things like that. If we can deliver the drug only to the place where, for example, the tumour, then we can get rid of those side effects and we can improve the action of the drug. So drug delivery is a very important area. And in nanotechnology in particular, gives us the opportunity to package the drug up in sort of small nanoparticles. And we make those nanoparticles smart by putting molecules that recognise the tumour, for example. So when you inject those nanoparticles with the drug payload, they can deliver it to that one area. What's kind of interesting is when you look at nanotechnology in the sort of wider sphere, people often see images of mini submarines running around our bloodstream and perhaps attacking bad cells and delivering. And really that's kind of unfortunate, because what that's giving the impression of is that we're kind of taking a traditional engineering approach, like taking a submarine and just miniaturizing it. And that's really not what nanotechnology is about at all, particularly in drug delivery. What we're doing is creating objects from the ground up, as it were. And biology is all about soft, things are moving. It's not about sort of an engineered mini submarine. What we're creating is these smart nanoparticles which have very fluid motion. The molecules on it are always moving. It's not about miniaturizing something we're familiar with. It's about creating a whole new technology by building things from the bottom up. What we would say is self-assemble, things that come together to form these objects to deliver that drug. Not about taking an object we're familiar with and kind of somehow making it smaller.